Okay, so ഈ മോഡ്യൂളിന്റെ ഫസ്റ്റ് പാർട്ട് എന്ന് പറഞ്ഞാൽ ഒപ്റ്റിക്കൽ കമ്പോണൻസ് ആണ്. സോ ഇൻ ദിസ് ലെക്ചർ ദ ലേണിംഗ് ഒബ്ജക്റ്റീവ് എന്ന് പറഞ്ഞാൽ രണ്ട് കാര്യങ്ങൾ മനസ്സിലാക്കുക. ഒന്ന് ഡയറക്ഷണൽ കപ്ലേഴ്സ്, രണ്ട് മൾട്ടിപ്ലക്സേഴ്സ്. രണ്ടും തമ്മിൽ although they are two different topics, the multiplexers also include some kind of a directional couplers. So we are going to see different types of optical directional couplers and optical multiplexers. Okay, so first we are going to look at the directional couplers. Directional couplers പല രീതിയിലുണ്ട്. So what you mean by a directional coupler is a coupler is something in which you can direct the power. For example, let's say I have a source like this. It can be an optical source. Okay. Now I want this the optical radiation emitted from this optical source to reach multiple destinations. Okay. Now basically then I want to direct this power or direct this radiation to all these different destinations. Chumma direct ചെയ്താൽ പോരാ, it should be directed in such a way that you should be able to transfer the maximum power in all these directions. Okay. Now the problem is, now you need to construct some kind of a structure in which when the wave propagates in through different branches, it doesn't cause too much of loss to the wave. Now the main property of any kind of electromagnetic wave is electromagnetic waves always dislikes discontinuity. The wave always wants to travel in a unbound medium without any kind of obstacles. So if it sees an obstacle or if it sees any kind of a discontinuity, so discontinuity is, for example, in this case, you see that the wave can travel straight and then it need to bend to direct the wave to a different destination. Similarly, there's a bend here, everything. So all these are different types of discontinuities. And whenever it sees a discontinuity, the wave always tends to lose some kind of power. It can be the loss because of like a reflection, or it can be a loss because of radiation spreading out. So all these different kinds of problems will happen. So we want our wave to travel through the discontinuity and reach the destination as much as the incident power. So whatever power is incident, it should reach there at the destination. But it is always not practically possible. You will always have some kind of a power loss or insertion loss, etc. And also, see, if you want to create a structure like this, for example, to direct different waves, then the problem again is you need to have some kind of a mechanism here where it branches out, in which it needs to have something like this. So you have this guide here, then you need to have some structure here which allows you to branch out in different ways. Okay, so this is a different optical component you need to insert, and this optical component for itself will have some kind of a loss. So all these factors will come into picture when you try to direct the power to different destinations. So the coupler or the directional coupler are the different type of optical components which helps you to direct the power with minimum power loss. So the most common is 2x2 coupler. So 2x2 coupler, you see you have two inputs here. You can give the wave as two inputs, and there is a small coupling length here. Okay, so coupling length means I can get the power come here, it can go to the bottom coupler and move out, or the bottom power incident light can move to the top and move out. So these are the output and this is the input. So you can direct the wave, which is coupling at 1 or 2 to 3 or 4. So 1 can move to 4, 1 can move to 3, similarly 2 can move to 3 and 2 can move to 4. So basically there you can change the direction of optical power. So if you look at the block diagram, so these are x1 and x2 are the two inputs. Now A11, A12, A22, A21 are actually the scattering matrix parameters. And depending on the value of each of these parameters, you will be able to transmit a fixed amount of power from x1 to y2 or y1. Also a fixed amount of power from x2 to y1 or y2 depending on this parameter values. So this is called as a 2 by 2 coupler. There is another coupler which is called as Y coupler. So you see that the shape itself is some kind of a Y shape. So this is an input fiber where you will input the signal here. Okay, and the signal will move here. Now signal sees a discontinuity because now it needs to change its direction like this. Okay, so there is a possibility of loss in Y coupler. So Y coupler has always a good amount of loss and it can move out of the two branches. So usually in Y coupler, we will have a small region in between the Y shape, which has a refractive index of mu3, and mu3 will be much less than mu1 and mu2. Why? Because if you have high refractive index here, there will be huge loss of the wave which is being separated at that junction. So you usually have a small refractive index to make sure that the change in the power when you separate the waves is minimum. So this is called as a Y coupler. Now there is something called as a star coupler. Star's configuration is a configuration in which if you have, let's say, two inputs or let's say three inputs and let's say five outputs, then it is possible to direct power from any input to any output. We can direct power from any input to any output. Similarly, from second input to any output, third input to any output, etc., etc. This is called as a star configuration. Okay. Now the star coupler does this trick. So how does it do is like, so here you give the inputs. There's a mixer rod here which mixes all these signals. Okay. And then depending on the configuration, it will be able to direct the signal from these inputs to any of the outputs here. Okay, so there's a configuration that you can do in the mixer rod by which you can direct, for example, the input at the first point to either output at 1, 2, or 3, or 4, anywhere. So this is called as a star coupler. Now here in this is called as a transmissive star coupler because you have an input port and you have an output port. There is another coupler, something called as a reflective star coupler. So here, instead of an output port, or input port, you have something called as a mirror. Now, the good thing about this is you can always use the input port as the output port also. So you can give in the signal through this input port. It will get mixed in mixed rod. It gets reflected using the mirror, and using the configuration of mixed rod and mirror, then you can direct this input to any of the outputs. Now the problem with this reflective star coupler is it has a less efficient manner because of there is a mirror at the one end. The mirror reflectances cannot be made 100%. So some amount of loss will happen in this mirror. But you can use the same input port as output port also. So that's advantage. This is called as a star coupler. Now another type of star coupler is fusion method star coupler. Here you can see that you have this 8 inputs here, 8 outputs here. Now there is a small coupling area here, which is called as a fused section. Now fused section is in which when the wave travels through any, let's say through the one, it can get fused, means it can get absorbed into the next or any of the output lines. Okay, so because of this tightly wound structure here, you can configure in such a way that the input can fuse into any of these output lines, and thus the output can go to any of the lines. Okay, and this is unidirectional. Like you cannot make input here. The input should be given from the left side, and the fusion or the mixing will happen in this coupling area. Okay, this is called as star coupler using fusion method. There is 8 by 8 star coupler. Okay, again, you can start from the first position and you can reach 1, 2, 3, 4, 5, 6, 7, or 8. Similarly, you can start at 8 position and you can reach any of the 8 position. Now, in this 8 by 8 star coupler, you can see it's some kind of a butterfly diagram that you have studied in FFT. Okay, so you have a 3 dB coupler here so that you do not lose power. So for example, if this is of a very large length, then the possibility of power loss is very high. So in to make sure that there is less power loss, you will have a 3 dB coupler so that you will just amplify the signal a bit in this coupling area, and then you will pass it to the other next stage. So there are 3 stages here because of it is 8 by 8. Each stage you have some kind of an amplification and a coupling happening so that the power loss from the input to the output is minimum. And again, you see that because of this butterfly structure, you will be able to direct the signal from any input to any output. This is called as 8 by 8 star coupler. Then there is free space star coupler. Again, in free space star coupler, instead of, or you can say that there is a free space because of this small box. Okay, and you can direct the beam from any of this input coming to any of the outputs. Okay, so why it is called as free space is this is a free space region, and using the free space region you can couple with it. Now in other couplers, it might be possible that the whatever region or the media inside the coupling region might be different depending on your application, and depending on the media there can be a huge loss or less loss. Now since it's a free space region, now the loss will be less because usually the wave travels with maximum power in a free space, and using that free space region you can change the direction of the input power or input radiation to any of the output ports. Okay, so this is some kind of a waveguide array, this output and input. Now let's look at multiplexers. The multiplexers is similar. So if you have looked at all these coupling things, you see it's a kind of a multiplexing operation also. Multiplexing means you are having an input which is directed to a different output. For example, in star coupling, you are having an input which can be directed to all the outputs. So it is called as a multiplexing. So demultiplexing and multiplexing is always used interchangeably. So if I say multiplexing, it can be demultiplexing also. So whenever you have an input at any one of the port, it can be directed to the output port. So in logical systems, multiplexing is something like this, where you have an input here, you can direct the input to any of this output. Okay, and demultiplexing is the opposite way, where you have an input here, you can give the input here, and it can be directed to here. So all these inputs can be directed to a single output. This is called as demultiplexing. The opposite direction is called as multiplexing. Now, in optical system, we do something called as wavelength division multiplexing. Okay, so in wavelength division multiplexing, so you might have studied about frequency division multiplexing, FDM. So what it does is, so you will have different frequencies, okay, and you multiplex. So the information will be carried in each of these frequencies, okay, and this information can be, so once it is carried, Then at the receiver end, this will be separated. So this will have one information, second information, and third information. So this is called as frequency division multiplexing. So you have different frequencies, and from different frequencies, the or information will be overlapped or superimposed. Some kind of mechanism is there in which you will put the information over the frequencies, and at the receiver end, you will separate it out for different frequencies. This is called as frequency division multiplexing. So in wavelength division multiplexing, you put the information in different waves, different wavelengths. Okay, so you can say the simultaneous transmission of many optical signals over the same fiber from different sources with properly spaced peak emission wavelength is referred to as wavelength division multiplexing. So you have multiple signals. So let's say your wavelengths are lambda 1, lambda 2, lambda 3, etc. For example, lambda 1 might correspond to a bit of 0, 0, lambda 2 is 0, 1, lambda 3 is 1, 0, lambda 4 is 1, 1. For example, just for taking a digital transmission example. So in this case, you will mix all these signals at a time. Okay, so lambda 1, for example, something like this, lambda 2 is something like this, lambda 3 is something like this. So all these signals will be transmitted at the same time. So you see that each of this wavelength will actually represents a different bit pattern, and that can be transmitted. And at the receiver end, you need to separate these wavelengths so that you can retrieve back that bit pattern or the information. So in principle, WDM scheme is same as frequency division multiplexing used in microwave, radio, and satellite systems. The difference between them is the spacing in the wavelength or frequency domain. WDM is coarse, while optical FDM is fine. Fine means it will have a very narrow range, but wavelength division multiplexing will have a very large range. Now, WDM devices can be unidirectional or bidirectional. So in unidirectional device, it is used to combine different signal wavelengths onto a single fiber at one end and to separate them out into their corresponding detectors at the other end. So unidirectional means you have a single uh, signal coming, which is a combination of multiple wavelengths, and at the output, you separate it out into different wavelengths. A bidirectional device is used to send information in one direction and simultaneously receive information in the other direction at different wavelengths. So in bidirectional device, you combine all the wavelengths, you send it through the fiber. Now, during its transmission, you might have some kind of a receiver or some kind of a mechanism in which you will be able to identify each and every wavelength. And then you can combine back it again and send it back so that at the receiver end, finally, it will still be a mixed wavelength type. Now, the word multiplexer is often used as a general term to refer to both multiplexer and demultiplexer, except when it is necessary to distinguish the two devices or functions. So this is same as that of uh, what I have said earlier, because you can always use multiplexing and demultiplexing interchangeably. Okay, fine. So this is a block diagram of unidirectional and bidirectional multiplexer. So the first one is unidirectional. Okay, so you see that the direction is always from left to right. You have different wavelength sources, lambda 1, lambda 2, up to lambda n. You have a WDM device, which will combine lambda 1, lambda 2, up to lambda n. And then it will be transmitted to the fiber. At the receiver end, you will have another WDM device, which will separate out or detect each of the different lambda 1 to lambda n, so that you will have the corresponding signals. Okay, and in bidirectional, you see that you can start from left, go to right, or start from right and go to left. So in both ways you can do the same. The blocks inside is exactly same. You will have a source which can make different wavelengths. It can be combined in WDM device. It will transmit. It can be detected. Individual wavelengths can be detected, and the output signal will be there. At the same time, you can also give an input from the detector or input from the side in which you have detected the signal. You can combine the wavelength, give to WDM device. It will make a combination of all the wavelengths, transmit to the fiber. This WDM device on the left side will separate all the different wavelengths and give to detector and gets the output signal. This is the unidirectional and bidirectional case. Now, the three basic performance criteria for wavelength detection or wavelength diffusion multiplexing or demultiplexing is insertion loss, channel width, and crosstalk. So insertion loss of a WDM device includes connector/splice loss of the device to other fiber and intrinsic losses within the device. So insertion loss means you have one fiber through which the wave is coming. Now to combine or to separate all these waves coming using a WDM device, the WDM device should be connected to the fiber using some kind of a coupling device. Coupling in the sense like something or a connector. So there can be a connector here which connects the fiber to the WDM device. Now this fiber, because of there's a discontinuity between the WDM device and the fiber because of this connector, it will cause there is cause a loss in power which is called as insertion loss. Okay, and similarly there can be many losses inside the devices and the fiber which is called as intrinsic losses. Okay, this all contribute to the insertion loss. Now channel width is the separation between adjacent carriers in the wavelength range that is assigned to a particular optical source. Okay, now you see that if you plot the different wavelengths that you use, so you'll have lambda 1, lambda 2, lambda 3, etc. Now there is a separation between lambda 1 and lambda 2. This is called as a channel width. Okay, now if you make channel width very less or small, the problem is to detect different wavelengths, it will be tough. It can be detected, but it will be detected with some kind of an error. So you should have the channel width as maximum as possible. So channel width needed for laser diodes is of the order of nanometers. In case of LED, this order of hundreds of nanometers. So laser diodes use very small channel width because the frequency is large, and LED use very high channel width. Okay, and crosstalk is basically the noise. So when the wave passes through the fiber or through the different connectors or to the WDM device, there will be interference from an external environment. It can be of different fiber, it can be of different device, etc., etc. So all this will contribute to the crosstalk, and you should always keep it below minus 30 dB. For preventing the entry of wrong signals into the receiving channel, the following precautions are to be taken. Demultiplexer design must be perfect. Stable optical filters with sharp cutoff should be used. So the first one is trivial because if you make a imperfect design for demultiplexer, always there will be loss. The second case is, now you see that you have the fiber and your wavelengths are coming, lambda 1, lambda 2, lambda 3, etc. Now if you want to detect any particular range of wavelengths, okay, now wavelength correspond to some kind of a frequency, so you will design some kind of a filter which will cut off all the wavelengths within this range of this filter. Now ideally the filter should be something like this with a sharp edge. If the edge is not sharp, all the noises or the crosstalks or the interference signals coming to this wave will also be detected. and this will cause problems in the final detection. Okay, so the filter should be as sharp as, or you should have sharp cutoff edges. So for directional couplers, WDM device can be classified as follows. So WDM device can be used as directional couplers also. It's bulk type, fiber type, and waveguide type. So this is bulk type. It's called as green rod lens. You see that you have input here, which gives wavelengths lambda 1, lambda 2, lambda 3. So you have a pyramid-like structure called as reflective grating along a slope. Now, when the wavelength is incident on any of this refraction grating, depending on the wavelength, it will get splitted into different wavelengths and it will come out of different output ports. So you see, actually you are doing some kind of a coupling using this WDM structure. This is called as green rod lens. So I think this is the same slide. Now there is a dispersive device prism. This you might have seen in your physics classes in your +2 and first years. So if there's a prism, the prism will split the input signal into multiple wavelengths. For example, you might have seen in your physics class that if it is a white light, the prism will split into the Abibjor colors. Similarly, you can have a prism which, when incident by a wavelength of different values, can split into lambda 1, lambda 2, and lambda 3. There is dielectric thin film filters. So here, depending on this filter, when the wave passes through the filters, it will get separated into different wavelengths. Now so you should always design this filter correctly so that you should be able to separate the wavelength that you need. Okay, so if you have, so this is for only for 3 wavelengths. If you have more number of wavelengths, you need to put more number of filters for that particular wavelength so that it will get filtered out, and the rest of the wavelengths will transmit as it is. This is called as thin film filters. And this is multi-layer interference meter. So you see that in this case, you have a different refractive indexes. So we also know something called as total internal reflection. So when the wave incident light passes through it, since there is a change in refractive index in each layer, some of the wavelengths will encounter a total internal reflection. Okay, and this total internally reflected wave can be detected or can be collected to find out the signal. Okay, so this is basically works on the principle of total internal reflection. Then there is fused fiber coupler, similar to that we have seen here. You input a combination of different wavelengths and you will get an output of the wavelength separated. Okay, so there is a small region here which is actually the fusion region where the couplings are fused, and the fusion region will make sure that the different wavelengths are separated. And next is fused fiber coupler. Sorry, this is the same slide. And next is polished fiber WDM device. Again, you see that there's a core here. This is a single core. When it reaches here, actually there are 2 cores. Okay, and these 2 cores are spaced very close. The cores in 2 fibers come closer and coupling occurs between them after polishing the fiber side. So because of this closeness, there will be some kind of a coupling wherein which the desired wavelengths will fuse or couples to the other side. So even if there is a combination of wavelengths is coming, you will have 2 output ports which give separated wavelengths. And thin film filter, again, you have a filter here in this position which can filter the wavelength of your desired choice, and the other wavelength will come off the other end. Okay, so this is basically an optical fiber, and this optical fiber, inside this optical fiber, you will place this filter so that you can separate the different wavelengths. Next is Max-Snyder interferometer. Actually, this uses something else using the Max-Snyder interferometer. So what it does is, Max-Snyder interferometer is something which can detect a phase shift. So when you have two couplers here and two wavelengths is being passed, now because of these different wavelengths, the amount of phase shift because of the wavelength will be different for both of them. Okay, so one will have higher phase shift, other will have lower phase shift. So this can be detected and separated using the Max-Snyder interferometer. And this delta L dash is actually the length which is being traversed by each of the wavelength, and the phase shift is given by this length and wavelength. So depending on lambda, you will have a different phase shift. Okay, so two waves having a phase difference interfere at the second coupler. And you can have another situation in which this is actually a demultiplexer where you have different wavelengths being inputted and which can be combined to get the output. This is called as cascade of two wavelength WDM device. Okay, so here there's a circuit in which you will be able to combine all these wavelengths. Okay, yeah, so that's all for today. So in the case of waveguide type, you will have a the device looks something having a guide mode in through which the wavelengths can move. So it looks something like this. I'm not sure whether I will draw this. So inside this structure, there will be another structure like this, which acts as a waveguide. There will be another structure like this, which acts as the waveguide, and the fiber will be connected here. Okay, and there will be output fiber here. Okay, and in this section, so this input will be a combination of lambda 1 and lambda 2. So the output will have lambda 1 and lambda 2 separated. Okay, so there is a mechanism in which inside the waveguide type filters, there's a filter here which will filters each of the different waves. So there's a filter here which will make sure that lambda 1 will pass through this and lambda 2 will pass through this. This is called as a waveguide type. Okay, so I forgot to add the figure here. Fine. Yeah. So I think that's all for today. I'll also share a notes for this. I think I have some notes. Okay, so please go through it, and also please go through the previous lecture that I have uploaded. Um, and let me see if I can. I'll be giving you an assignment based on the last module, optoelectronic ICs, and maybe you can submit it within a week or something. Okay, fine. So I think that's all for the class today, and so Monday we'll have class, but we will not be having class on Wednesday because I have an election duty. Most probably, we might not also have class on Friday because next day of election. So so let me see if I can upload some lectures so that you can watch it and we can discuss it once I come back. Okay, fine. So let me take the attendance. I think everybody is present. What is the strength of our class? Just a second. Yeah, I think everybody is present. 37 is there. Okay, so I'll give attendance to all. Okay, fine. So thank you for listening, and we'll meet on Monday.